All right.
We'll wait for a minute so that everybody can join.
Absolutely. Let's give them 1 minute of grace for people to join.
How are you? People are still joining, so maybe 30 more seconds and we can start. I think we can start, Marco. You can take the lead.
All right. Thanks, Sam. Then good morning, good afternoon, and good evening, everyone, depending on where you are. My name is Marco Ranalli, and I'm Business Development Director at Global Immersion Cooling Association. We have a quite dense schedule today, so let me quickly move on with introducing who's participating, the hosts of this webinar organized by the Global Immersion Cooling Association. So with us, we have Arnaud Desrand, who is president at the Global Immersion Cooling Association, Toby Rockstraw from Shell, Sean McBride, standardization manager at JICA, and Alison Byrne from Alcatex, and Jean-Marc Denis, chief product officer at Submer. So we have very interesting participation also from the host side. I will not steal too much time to the presentation because I'm sure there will be a lot of questions. Even if please feel free to add your questions as they come on the chat. We will try to address some of them at the end of this webinar. But in any case, we are going to answer to all of you in a separate session offline for the benefit of all the participants. So quickly on the agenda. So the topic today, as I said, is very dense of content. A quick introduction about the Global Immersion Cooling Association. We'll focus and recap on what's happening on the EV and the HEV industry, and also we took the opportunity to give Shell a small slot to introduce the most recent Triple 10 initiative. We will move on, and you will notice how the same rationale is behind what is happening in the EV industry and what's happening in the BESS and data centers industry. So we'll move on with the data centers BESS cooling report, and conclude with the latest initiative from the Global Immersion Cooling Association, which will be introduced by Sean McBride and is focused on standardizing immersion cooling solution across industries. Quickly about GICA, as we call it, some of us, Global Immersion Cooling Association, is a non-profit organization with the goal of accelerate global adoption of immersion cooling and enhance energy efficiency, reliability, and environmental sustainability. The three main areas where we are active is in standardization, of course, across industries, like as mentioned before, industry education, and as this webinar as an example about how we are trying to push and share knowledge and disseminate knowledge about immersion cooling across industries. And as part of that, of course, the global networking and the establishment of collaboration framework with all the members or parties interested in collaborating. The situation today, so GICA was established last year, but we have already very good and active members in covering different areas. You can see here, for instance, covering the dielectric fluid area, companies like Shell or Castrol or Phillips 66, Inventec, or NOAA. But we have also component manufacturers like Caltex, Moltec, or Lightens, and even system integrators like Carrar and XOS. And on top of that, across the board, companies supporting development activities with testing like ATA, APL, or modeling activities like Gamma Technologies. We are very active also with our affiliations with automotive suppliers or the unmanned vehicles like C and or locally with the next generation manufacturer in Canada. But of course, also we have a very strong connection to the OCP Open Compute project, as actually, as you will see through this webinar, this is the area where immersion cooling is more mature in terms of technology. Just the last slide, just what are we talking about is when we talk about immersion cooling, we have several solutions. But typically we talk about full immersion cooling, which is the area where most of the players and companies are active today. You just see a fraction, a portion of those in below. There are some exotic solution like spray jet cooling, where Valeo is active, and let's say in the cutting edge of technology. We have also two-phase cooling, where the fluid changes phase from liquid to gas, and where we still already have companies very active in that area. And of course, across the board, as mentioned before, companies who are providing solutions for all architectures. At this point, I will let Sean McBride, our standardization manager at GICA, to take over and tell us about what's happening in the EV industry. Sean, you there?
Yeah, Marco, thanks very much. So you can go ahead with the slides. And good morning and afternoon and evening to everyone. So in the next few slides, I want to give some context, first of all, to how immersion cooling has been adopted in automotive and non-automotive or other industries, and how also the motivations for that adoption and implementation is developing, both on things such as performance, safety, and future drivers that are related to that. So going back a few years, or going back to the beginning, let's say, in automotive terms, this is the first example of the implementation of immersion cooling in an automotive system. This was a hybrid supercar from Koenigsegg, which featured an immersion-cooled battery for the hybrid drivetrain. This was an 800-volt system, and used immersion cooling along with 3 electric motors and an internal combustion engine. In these early applications, the main motivation and main driver, of course, for using immersion cooling was to reduce size, to have a compact system, but still to achieve, especially in this type of application, extreme high power density. So to be able to charge and recharge the battery at high C rates, and immersion cooling was a key enabler for doing this. Also, not just once or twice, but in a repeated and high frequency application. There are also other examples. So if we move on to 2019-2020 period, then you'll see, for example, the McLaren example. Marco, you can move the slide. I'm not sure if you've changed
it. No,
yet,
but it didn't, was stuck. Yeah, go ahead, sorry.
So an example again in a hybrid electric supercar application from 2019-2020, the McLaren Speedtail. Here in this application, the motivation is again the same, essentially. Very high power density achieved through the use of immersion cooling. In this case, up to 270 kilowatts peak power from a hybrid powertrain battery. That, of course, is enabled by rapid heat removal by the immersion cooling system. And again, same motivation, compact packaging enabled by the technology. Then slightly later, we see the same adoption and same motivations from Mercedes AMG. So in the period 2021 up to right now at this period, we can observe from Mercedes AMG 2 different immersion cooled battery systems, HPB 80 and HPB 150, both again for hybrid systems, and again putting out extremely high power for relatively small capacity. So in the case of the HPB 80 system, for example, that corresponds to a 6 kilowatt hours battery delivering 150 kilowatts of peak power, which equates to very high C rates of 25C. What's important to note here is that, of course, these are custom and relatively niche applications. But for example, in the AMG case, this is also adopted in extreme high demand situations like Formula One, for example. And in terms of the AMG vehicles, there are about 20,000 vehicles on the road as of today. So moving on, what we just looked at are examples of more niche and custom applications. But if we look at immersion cooling, so from a few years ago, but if we look at immersion cooling as of today, there are examples where we see that immersion cooling is a technology which is ready for series or high volume production applications. So this is an example from Total Energies where they analyzed the use of immersion cooling in 2 series production vehicle platforms. One case, the Renault Megane, and the second case, the Volvo XC90. They integrated an immersion cooled system without the need for vehicle redesigns, without changes to the platform. And in this project, they were able to validate all of the key metrics such as packaging, sealing, safety, and serviceability. On the right-hand side, you can see the comparison between the original Volvo battery, which is not with immersion cooling, versus the newly designed battery with immersion cooling, and how they were able to achieve the exact same, packaging solution with a different technology without made any platform changes. Okay, so that's some examples in automotive, but we can also see the adoption of immersion cooling, and this is very significant in other industries. So here you see examples from John Deere and Chrysler, who have a collaboration together for the implementation of a modular immersion cooled solution, primarily for construction and agricultural equipment. So this solution has been implemented by John Deere in tractors, excavators, mowing equipment. But the primary driver here, as opposed to the early adopters, where you saw the primary driver is, let's say, the solution which most people are possibly familiar with in immersion, which is very high performance, very high cooling capacity. But there are other motivators which are now becoming more and more important. And this is one example of that, where in a very harsh environment, construction, agriculture, under harsh conditions, lots of cycles and so on, the immersion cooling solution allows to implement electrified architectures without battery degradation. So extended lifetime, increase in robustness, and as well as that, increase in safety. And whilst also, for example, if we look in more detail, enabling downsizing of auxiliary equipment related to the thermal management system due to better heat transfer that can be achieved with immersion cooling.
Okay, and I think, Sean, we are going to find a way, again, this topic of reliability also in other applications, especially, I don't want to spoil the presentation, but Jean-Marc from Submer will talk more about that and how important it is in other industries like for data centers and AI processing. Before we leave the EV section, I would like to give the word to Toby from Shell and let him tell us about the new initiative, this Triple 10 initiative at Shell. Toby, are you there?
Yes, I'm here. Can you hear me? Thanks, Marco. Yeah, thanks for the opportunity to speak here. So on April 22nd, we may have seen it in the media, we made the announcement that we will be launching a prototype demonstrator, let's call it vehicle, B-segment vehicle, which will have, it's called the Triple 10 Challenge, meaning that it will have a carbon footprint of 10 tons, below 10 tons, energy consumption being at 10 kilometers per kilowatt hours, and then also a charging time of 10 minutes in under 10 minutes from 10 to 80 SOC. That's the challenge that we set ourselves, and we'll be launching that vehicle in mid of June. So over here, because we're talking about fluids, immersion fluids, here's a simplified single fluid circuit that exists in the vehicle. All the block boxes that you can see that are in that sort of turquoise green color, they indicate where our thermal fluid is flowing. And then the gray section there is the refrigerant circuit. So as you have in conventional battery electric vehicles, you'll have this refrigerant circuit that also feeds into the onboard HVAC system that is used to sort of pre-chill the battery during charging, or precondition it, if you will. What we've done here is to replace the entire fluid circuit, which is normally water ethylene glycol, with our thermal fluid. So basically it's an immersion cooled battery pack, and then we use that same fluid, part of that same fluid, to cool the motor and power electronics of the motor, so the inverter, as well as the onboard charger, DC-DC converter. And then we reject that heat via a conventional radiator. So there's nothing special. This is a radiator that can also be used for water ethylene glycol. And that's the circuit. If you go to the next slide, there's a bit of a video. It should work, hopefully. It shows the sort of bit of sound as well. So you can see the build-up. That's the power unit. The power unit there again. You can see the radiator on the left-hand side, and then the blue, turquoise blue. Those are the cooling circuit. Thank you. Cooling circuit. The packs in the back there. It's quite loud, actually. The packs in the back there are the two battery packs. We're talking about around about 30 kilowatt hour battery pack. The reason why we can do with a 30 kilowatt hour battery pack, which is quite small by comparison to other current BEVs, is because we have a very light vehicle, and therefore we can have acceptable range with a small battery pack. And the immersion fluid enables us to recharge the battery at a very swift rate, even though the battery is small. So we can put comparatively a lot of power into the battery cells and maintain the battery temperature. What we have here is
the immersion cooling enables this fast charging, which otherwise wouldn't be possible in normal situation. Okay.
Correct. Way higher than conventional water ethylene glycol currently. And then the trick is also because automotive manufacturers are hesitant to employ two separate circuits of water ethylene glycol for the power, for the traction motor as well, power electronics. We're using this one coolant loop, so single cooling fluid, which is the enabler here, and that's again enabled by our thermal fluid. So what you see here we've done some tests together with Aruba Myra on the VTOS rig. So it's a test rig where you can basically set up all the components in the thermal system. So basically radiator, pumps, valves, etc., that will cool the battery as well as the traction motor. And what we've shown here is that you can do a comparison, because water ethylene glycol is obviously our baseline, and we all know that water ethylene glycol is a very good conductor of heat. So it's very effective that way. And our thermal fluid is also, everybody knows that it has a lower heat capacity rate. It also has a lower heat transfer coefficient. However, if you look at the overall system, the keen-eyed will see that the normalized heat transfer that's given here in kilowatt hours per Kelvin effective temperature difference. So that's the temperature difference between the air as well and the working fluid or the cooling fluid, being water ethylene glycol or thermal fluid. What you can see in there, it's by no means half. It is around about 70%, 73% in fact, is of the thermal of the heat capacity, heat rejection rate of the radiator is still achieved with the thermal fluid, and that is borne by the fact that in the overall system, there's thermal resistance between the fluid to the surface, and then there's conduction through the aluminium that's negligible, but then the surface to air rejection rate, that is pretty poor, because air is a very poor heat conductor, and therefore it's basically mutes that overall sort of loss in thermal heat transfer coefficient. It's actually masked by the fact that we have to reject to the environment, and therefore it doesn't look all that bad at all. Let me go to the next slide, if I will. This is actually last slide. So here, another interesting, we've presented, this was also presented at the Vienna Motor Symposium, end of April. So those who are interested will also be able to find more detail about the specific study. We did some driving simulation studies, and we also did some charging simulation studies. And this one is quite interesting, because here we plotting the heat rejection as well as the cell temperature in the battery during 10 to 80% charging in the 10-minute time period. So the two lines at the bottom, so they go up to 20. So if you go to the lines that basically jump up to 20, that's 20 heat, 20 kilowatts of battery heat, right? That needs to be rejected, and basically drops off a little bit due to the charge curve, the current curve that we're subjecting this battery to. And on the other plots, the other lines at the top are the temperature with the chiller on. So that's the refrigerant circuit on, temperature with just the radiator fan on. And the third one is the temperature with none of these systems running, just pumping the fluid through the radiator, not actively rejecting the heat. And what we show here is that starting at 25 degrees centigrade battery temperature, one is very comfortable, so the thermal inertia of the system plays in our favor, because we are able to absorb all the heat that the battery cells generate. We're able to absorb that in this coolant circuit, and we still maintain, let's say, about 53, 52 degrees centigrade, even without any of the additional systems running. And obviously, if we want to push that system further, and we want to charge even faster, or we have a bigger battery, if you will, then you can then start implementing the radiator fan and reject more of that heat. And if need be, or if you start at the higher temperature, you can also switch on the chiller, and then you can very effectively reject that heat. But the first one is very interesting, because when you've seen battery electric vehicles charging at high power, when you stand next to them, and especially in the front, you can hear that radiator fan going full blast, trying to desperately reject that heat. And the immersion cooled system is it's a very nice system in that you can basically absorb that and then reject it at your leisure when you're driving off, and use the wind from the driving to reject it. And I think that's my last slide on that one. I think.
Perfect. Okay, thanks a lot, Ruby. I think it's performance is one point. The other aspect we want to close with is this EV section is the safety and reliability. I'll ask Sean to comment the next point.
Yeah, exactly, Marco. So we presented already the early adoption of the technology, how that was motivated around early, performance in comparison to other technologies. We've talked about how immersion cooling is not just about performance, but also enabling lifetime. And for example, that's demonstrated, and robustness demonstrated by adoption in, for example, off-highway applications, construction, and agriculture. If we come back to the specifically automotive case here, then we, and specifically obviously electric vehicles, look into the future and look into how do we marry the expectations in terms of performance and next generation versus the requirements in terms of safety in particular. So on the left, of course, we see that the newest generations of EV architectures and batteries are striving towards higher and higher charging rates, target implementation of 1 megawatts charging. For reference, only a few years ago, charging rates of, let's say, about 250 kilowatts was considered to be extremely fast charging. So this is obviously a massive step up in performance requirements. That equates to, for example, if we say, okay, we have a benchmark which is 2 kilometers per second for 4 minutes, that's an objective of achieving 480 kilometers of range in 4 minutes. So obviously that requires very high current and stresses the battery a lot and requires a lot of performance from the thermal system. On the other hand, the new GB 38031 2025 requirement in China, which is due for adoption in July of this year, completely also increases the requirements from a safety perspective. So you may be familiar with previous thermal runaway requirements, whereby it was considered acceptable for a 5-minute warning to allow occupants to exit the vehicle in the case of thermal runaway of the battery. Now, this previous 5-minute requirement has been extended to 2 hours requirement. So there should be no fire for at least 2 hours. And this really creates the requirement of preventing thermal runaway propagation. That is to say, preventing the, if one cell is triggered for some reason, that this doesn't pass to the neighboring cells in the pack. So using conventional solutions, by that I mean especially cold plate solutions, we have to think about not just preventing the propagation, but also managing gas venting, for example, the actual inherent limits of the amount of heat that can be extracted from the cells through a cold plate solution, thermal interfaces, and so on. And we also have to try and prevent propagation using mostly aerogels at the moment is state of the art. So this obviously results in quite a complex and expensive design, difficult to implement. By comparison, immersion cooling solutions are more inherently suited to meeting this requirement. We've shown already how immersion cooling enables high performance, but also it's more inherently suited to high safety requirements as well. So the next few slides show briefly 3 examples of real-world tests where various partners have demonstrated how immersion cooling can enable safety requirements meeting the GB 38031 2025 requirement using different trigger mechanisms. So for example, here you see a test by BP and XOS where they demonstrate using a prismatic cell NMC module and a nail penetration test that puncturing a particular model, so in cells, so inducing a thermal runaway situation into one cell via nail penetration does not result in thermal runaway of the, in this case, example module. So the adjacent cells continue to operate within their temperature limits. The next example is a 2-phase immersion cooling system, this time Carrara in conjunction with Volvo. Slightly different because we also have cylindrical cells in this case. But again, the outcome is the same. The trigger mechanism here is different. This is an example where the trigger cell is triggered by over voltage as opposed to nail penetration. But you see again that the neighboring cells, in this case, they barely react at all to the thermal runaway of the trigger cell. And also you can see that because this is a two-phase system, the two-phase immersion system generally enables even higher heat transfer rates. So the actual normal or nominal operating temperature of the cells, in this case, you see the green dots in the image, which are the surrounding cells, is slightly lower than it would be with a alternative solution, especially with a cold plate solution. And the third example, again, is in this case Shell and XOS. Here there was a test which directly compared a cold plate solution to an immersion cooled solution in an A/B comparison. And in this case, the cold plate solution failed the test, whereas in the immersion cooled solution, there was no thermal runaway propagation, even with large NMC cells. So I think that concludes this section.
Thank you, Sean. I think it's a good point you raised about safety and reliability, which is a good introduction to the next topic. And I know maybe you can comment this, where safety and reliability are of paramount importance, in particular for battery energy systems which are using immersion cooling. I know you want to make a point on this?
Yeah, sure. So it's a good transition between the on and off-road applications and the data centers. This application, the battery energy storage system, is a stationary application, and there were a lot of fire that happened in China, especially in the last 3 years. So regulation went stricter 1 year and a half ago. And then there were a big move from air cooling for the BESS to immersion cooling. And here you have an example with the company Etika AG, who is a partner of Shell, that provides, let's say, BESS cooled with immersion cooling with an unrivaled safety. And the risk is really contaminated at the module level, so that is, if in case of any thermal runaway, because you cannot forbid any cell thermal runaway, you are sure that you have no contamination from one module to the other, so from one battery pack to the other, and therefore the entire container does not burn, which is unique because with the other technologies, when there is a thermal runaway, generally for the BESS, the complete container burns. And we are talking about 3 to 5 megawatt hours energy in the maritime containers. So it's a lot of energy that can burn. So it's not only dangerous, it's a loss of capex and loss of profit generating if a fire happens. Okay, so this is what we see now in the BESS in China. We estimate that 5 to 7% of the new BESS are cooled with immersion cooling, which begins to be a very large market because the BESS market in China is really large and increasing every year.
Okay. Thank you, Arnaud. And we are moving away from EVs and also moving away from energy storage technologies, so lithium-ion cells, because the immersion cooling is also of a great importance in data centers. And I will ask Jean-Marc to comment this or explain us what's happening in the market, the situation, and the reason behind this evolution in the data centers world.
Thank you, Marco. Thank you, everyone. And I'm very, very happy to be with you today this is my first participation to this webinar format. So I'm sincerely happy to be there. I am discovering a new usage of immersive cooling I did not know. So for me, it's a great source of information. So I'm Jean-Marc Denis. I'm Chief Product Officer at Submer, which is one of the world leader in immersive cooling in data center. The company has been created 11 years ago in Barcelona, Spain. And we've been focused exclusively on immersive cooling in data center. And during 10 years, to tell the truth, immersive cooling has been restricted to a niche market in the data center because people were a bit concerned with the usage of a liquid to cool IT equipment. So it was not a real industrial approach, much more psychological constraint. Because when we see, and I'm going to elaborate on that, when we see the evolution of the cooling constraints on the IT equipment for the coming years, this is the right time for immersive cooling, and we see immersive cooling becoming massive in the core data center. And when I say core data center, I'm talking about what you can see on the newspaper. This is the data centers for the hyperscalers, for the neo clouds, in the range of tens to hundreds of megawatts. And people are starting to talk about gigawatt campus, which is a giant. And when we see the evolution, the year-to-year evolution of immersive cooling in the core data center from 24 to 2035, depending on the scenario, it's very, very, very likely that we'll go north of $1 billion of revenue for the immersive cooling market in a data center before 2030. And it could even happen that we are north of 3 billion euro in that time. So this is big. And the split is very, very much aligned with the locations where the big data center are installed. This is North America for 1/3 of the market, Europe and UK for 1/4 of the market. So the combination is more or less 60% of the market. So this is massive and it's growing very, very fast. So the year-to-year evolution is 20%, which is, well, let's say for people more familiar with financial numbers, it's a very impressive number and it is attracting investors those days. That is very important for a very traditional technology. So when we look at the top reasons, and we could transition to the next slide, explaining why there is this momentum around immersive cooling. It's quite simple. If you consider that right now, you've got about maybe 90% of the data centers still operated with air cooling. Immersive cooling is bringing a new class of cooling technology where you can run almost always in free cooling. You can dedicate your energy, your electricity to compute. So for AI, 1 watt you save in cooling is 1 watt of additional intelligence to your AI activities. So this is big saving for the data center operators, say the neo clouds or the AI companies. Just to say a few names that you know, it's Anthropic, it's OpenAI, it's XAI, all those giants, they start using immersive cooling. And with this split, and this is a small picture on the top right-hand side, you can use electricity for cooling for less than 2% of the equipment with classical chiller. All the rest can be operated in free cooling. And so this is the evolution, the dramatic saving in PUE on energy. You have also, and this is crucial for the giant data centers, a much higher density per square feet or square meter, because you save a lot and you can densify, you can pack more servers in a smaller environment. This is a big saving in terms of real estate, in terms of operations. So big saving on any aspect. Something that is super important for the operators, and this is something they have discovered recently with immersive cooling, and this is exactly what has been explained before for electric vehicles. You bring better thermal stability with a heat spreading that is very low because of the thermal inertia of the fluid. To give an order of magnitude, in an immersive cooling tank, a standard tank that you can see on the picture, the quantity of fluid is about 1,300 liters. So I don't know in gallons how much is it. Maybe something like 300 gallons or 400 gallons. I never know. Sorry. But this is a significant quantity of fluid, meaning the thermal inertia is very significant. So for the very high-end GPU devices with super short thermal cycles, it helps a lot to stabilize the temperature, to reduce the thermal stress on the motherboard, the GPUs, on the IT equipment, so to improve the reliability of the system. And if you translate that into real operations, when you train a giant model, you need tens of thousands, if not hundreds of thousands of GPUs to train your model. If one GPU fails, you need to restart your training. Period. So it's a massive waste of money for, let's say, OpenAI when they need to restart the training of a model. With immersive cooling, more reliability, more stability, and they have much more chance to complete the training phase. And the training is not something you run one over a few months. This is a continuous training to always improving the quality of the models. This is just like the agile model in software development. This is exactly the same way they work. And doing that, they save a lot of money and they gain competitiveness against their competitor not using immersive cooling. So all in all, using immersive cooling, you have a much more simple infrastructure environment, a much better TCO against air cooling. And you can see on the picture something that is very modular, meaning it's very easy with immersive cooling to build modular pattern-based data centers from a few megawatts to hundreds of megawatts. And this is something that we're going to present on the next slide with a real concrete example coming from Viridien. Viridien is a French company, but that is operating in the US and in UK. And this is the #1 company in the world for seismic imaging. Their business is to take the data from seismic campaigns and to analyze the nature of the data and to detect where to drill to find oil and gas. This is their business. So their business is based on computation, heavy use of computation, continuous use of computation, 24/7 × 365. And being super efficient, super low cost is how they are more efficient than their competitors, and that explains why they own more than 60% of the market. And all the giant telco companies work with Viridien. So here, this is a picture of their data center in UK, 100% immersive cooling, 100%, everything. It's been built specifically for immersive cooling, and they started the operation in 2024, all using Submer equipment. Today, they operate 5 megawatts of IT load. It's not giant, but it's big on a pattern, and you can see the sequence of pattern in their data center. And they have in this data center more than 10,000 servers, and they run more than 25K GPUs. It's super stable, and they use a very standard Submer SmartPod EVO and EXO products. Sorry, it's a bit commercial at this stage of the discussion. But again, it's super important to understand that for them, they like immersive cooling because this is a competitive advantage.
This
And
is
for the anecdote, yes.
And Jean-Marc, I will stop you there because we are late in
Sorry.
time. But I think you made the point how reliability and cooling performance at the end of the day translates into commercial advantage. And I think this is the same for all the industries. I will maybe ask Arnaud to mention a couple of other examples of where immersion cooling has been used in the data center industry already, or where there's a background in that.
Yeah, sure. Thanks a lot, Jean-Marc, for introducing the Viridian case. And I just had a look to Claude Anthropic and OpenAI ChatGPT electricity consumption. This represents more than 30%. This is a minimum estimation of their expenses. So saving each percent here, we are talking about billions of dollars a year of expenses, if not more than $10 billion. So this is massive. Okay, so saving electricity here and increasing the reliability are really key. And here are just two other examples that we show here, but there are plenty of them. Alibaba Cloud. So this is immersion cooling is also used by majors. This is the main topic here since many years. And in that case, for Alibaba, this was single phase immersion cooling, full server submersion. To prove that, okay, the PUE, the annual PUE at the site level is below 1.2, and if you look at only the IT part, is more near 1.05. Okay. So this is proven to be reliable and they have a less issue than when it's cooled with DLC or air cooling. Next slide, please, Marco. So here, this is another initiative from Microsoft using two-phase immersion cooling, at least testing this. And this brings very, very impressive value in case of heat flux capabilities, because when the liquid is transforming into vapor, the heat transfer capability is increased by a factor of 1,000. So it's really massive. Then the question here for the adoption of this technology at scale is around the fluid use in that applications. And so the entire industry is waiting for real PFAS-free dielectric fluids. And this is where this is why it matters, but we know and hear that some chemical companies are organized to provide in the short term PFAS-free two-phase free dielectric fluid. So this is interesting to see what will happen in the future in that case.
So for sure, one of the challenges also our members faced every day for the future.
Sure, and then the last slide here is on NVIDIA liquid cooling strategy. You can find it on their blog. So NVIDIA, since a long time, has rejected immersion cooling because they have been investing heavily in DLC, direct liquid cooling, so cold plates, which will still be do the job for the chips this year and beginning of next year, but end of 2027, beginning of 2028 with Rubin Ultra, not only the chip but the entire server. This will start to generate some complexity if it's cooled by cold plate everywhere, because not only the chips are to be cooled, but also not only the GPUs, but also the CPUs, also the memories, etc., etc. So there are a lot to be done here, and maybe this will be hybridization technologies combining cold plate for GPUs, for example, for very high heat flux and high TDP, as well as immersion cooling for the rest of the server. This is things that we see more and more, hybrid cooling, including immersion cooling. And this is, NVIDIA is probably working on that kind of initiative. I will let the floors to Alison that knows more than us on that right after this slide. So here is just the last slide I will cover is around data center regulation in Europe, which will set up a challenge regarding the PUE below 1.2. So it's really hard to get it with air cooling, nearly impossible. So you need liquid cooling to get PUE lower than 1.2. And waste heat recovery that will start to be mandatory for sites exceeding 1 megawatt, which are really small sites in the data center industry. So nearly all the sites will be touched by this waste heat recovery that will begin to be mandatory with some percentage that will increase in the future. And the good news is that thanks to immersion cooling, you can better recover the heat because you can trigger the liquid temperature. Naturally, this can have an impact on the reliability and blah, 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 but you can play between 45 degrees Celsius and 60 degrees Celsius and therefore get a better heat recovery value thanks to the trigger of the temperature of immersion cooling. So yes, regulation will also help to push immersion cooling, especially the European regulation in the future. Okay, thanks,
Perfect.
Alison.
Thank you, Arnaud. And I will ask maybe Alison if she can tell us about what the OCP perspective is and what's happening from an OCP standpoint.
Yeah, absolutely. Thanks so much for having me. Of course, my company, Alcatex, we've been building and designing data centers for 30 plus years. I also work very closely with the Shell Lubricants team for their fluid family, including the single phase immersion cooling fluids. But actually, my passion is I've been working with OCP since 2018 in the immersion work stream, which is the largest work stream for OCP. More attendees. And of course, GIC has already noted at the beginning that they are collaborating with OCP. And that's really important because that OCP, those standards and the collaborations that create the standards really matter. And literally a year ago, June 2025, or almost a year, it was announced. And of course, this had taken several years to accomplish with the support of OCP, creating these relationships with Intel led regarding material compatibility and the guidelines that they wanted to put in place to achieve. And so that participation was with Shell, of course, for our single phase immersion cooling fluid, as well as Supermicro and Submer. And what that accomplished, again, after a very long and tedious amount of time, was the first fluid certification with full warranty for the Intel chips for an immersion cooling fluid. And it was quite the designation because that helps to solidify in the market the adoption, as well as some type of reliability that people can deploy this and receive full warranty for these solutions. And very, very pivotal place. We see a lot more happening in the next year in this. And so look forward to seeing all of you at the OCP Summit in October.
Perfect. Thank you, Alison. And I think none of this could happen without suitable fluids. So this is really the first step. And as a second step, certification and standardization is something we have to go through to enable fluids to be used across the industries. And it's actually the next topic Sean is going to report us about. Sean, you have 5 minutes maybe to go through this.
No problem, Marco. So exactly what Alison actually was talking about is a brilliant segue into these two slides. Basically, the very quick summary is that we, as GICA, the Global Immersion Cooling Association, would like to repeat the trick for not just data centers and from the OCP, but also into other industries as well. So essentially, as Alison presented, the data centers and open compute project area or arena is much more mature in terms of standardization than the other industries, for example, mobility, automotive, off-highway, and energy, which we talked about earlier. In data centers, there are already existing immersion-specific standards, and this is developed through primarily the Open Compute project, which Alison talked about. And there have been various revisions of those requirements since 2020. There are other related examples as well. For example, from the ASHRAE TC 9.9, which has explicit guidelines related to immersion cooling, and this has been implemented since 2018. On the other hand, in automotive and other industries, there are very mature safety standards. For example, I showed earlier around thermal runaway in automotive applications. So there are very mature safety standards in general in these industries, but there is nothing which is immersion specific. So that represents a gap and also an opportunity for GICA to play a significant role in transferring the maturity of data centers across to other industries. So in the interest of time, Marco, let's move on. Essentially, this harmonization of standards across industries should take the work of the Open Compute project as a baseline So just very briefly here, because we're running out of time, that would be related to things like material compatibility protocols, developing a harmonized cross-industrial test matrix of different fluids, materials, temperature, time, for example, a minimum spec of fluid qualification, operational and service procedures, how to handle fluids, and so on. The idea is that we should develop and implement these standards as annexes to the existing and well-established standards of each of the industries, so that we end up with something which is harmonized and cross-industrial. And obviously, the motivation is to minimize, for example, requalification burden, both for OEMs and suppliers and other stakeholders. So how do we intend to do this? We have established a Global Immersion Cooling Standards Working Group, which has already kicked off internally. And I don't see the next slide yet, Marco. So if you're trying to update, now would be a good time. Yeah. And so we are already starting this activity. And we want to ask everyone who's on this webinar, existing JICA members, and also non-members to consider to participate and to contribute. So there's a call to action here, obviously, to make this standardization process impactful. Then we need to maximize the outreach and maximize the contributions that we gain from everyone who has a stake in this solution and this industry. The objectives are to develop JICA standards. They should be harmonized and cross-industrial. And as I said, they should be structured as annexes to existing established standards in each industry. The overall impact, of course, is to try to accelerate the adoption of immersion cooling across multiple industries by leveraging on data center maturity. So finally, the industries which we have considered or are looking at the moment, of course, data centers, automotive, off-highway, battery energy storage solutions, unmanned airborne vehicles, marine. And of course, if there's someone on the call who's in another industry where immersion cooling is important or can be considered, but we haven't looked at that, then this is your opportunity to get involved and contribute. So we intend to look at various functional areas: safety, material compatibility, performance, for example, leakage rates, which is a very important topic in immersion cooling, test methods and recyclability, and so on. So we want this to be a very comprehensive exercise, and therefore we need everyone's contributions.
Perfect. Okay, thank you, Sean, and good luck with the standardization working group. We are really short in time. I just want to spend a minute on mentioning what's going to happen in coming months. As mentioned now, so we have already the standardization working group up and running, which meets every first Tuesday of the month. It's an online meeting, of course. What also is going to be started next month is the project group focus on the EU funded projects. So the idea is to create a consortium for the 2027 call for projects by the European Union, which involves advanced thermal management solution and thermal management solutions for backup energy systems for data centers. And I think we have here very, very substantial proposal. So in this case, we will talk about in the next opportunity. If you feel your company can contribute to this funded project, please write to us at info@jica.org. Let me also mention that we have fixed the date for the JICA annual conference, which is going to be in San Jose, in California, on October 12th, just one day before the OCP. So it's a great opportunity. If you're traveling to OCP, just join us at the JICA annual conference. And also for the automotive people, it might be a great opportunity to learn from other industries. So just you're of course welcome to participate. And also for this case, the write to us at the info@gcap.org address. We can talk about that. We will talk about that at the next webinar, which is planned in September. Now, I haven't seen how many questions, but all your questions will be answered. Let me assure you. We're running out of time, unfortunately. We will probably, like we did other times, distribute the list of questions and answer to all the participants so that everybody could benefit from this shared knowledge and the information which might interest everybody. At this point, so we are at the end of our webinar. Let me say thank you again to the hosts. Apologize for sometimes cutting short, but I think we are in perfect timing, and but it was a great contribution, especially from Alison, Jean-Marc, and Toby, and for bringing into this community that direct experience. So, and then of course Sean and Anu as and Saim and all the GCA members who participated to that. So thank you again, everybody, and see you soon at the next webinar.
Thank
Thank you, bye.
you.
Thank you.
Have a great
Bye-bye.
day.
Thank you, everyone.